In today's lesson, we're looking at the applications of the normal distribution. So let's take a look at General Electric. They manufacture light bulbs, and they have a decorative crystal clear 60-watt light bulb that it advertises will last 1,500 hours. Suppose that the lifetimes of the light bulbs are approximately normally distributed, with a mean of 1,550 hours and a standard deviation of 57 hours. What probability of the light bulbs will last less than the advertised time? Because you really don't want to advertise that, oh, they're going to last 1,500 hours, and then they don't. So let's think about how this would look if we were looking at the curve. So we have a curve here, normally distributed. The middle says is 1,550, and the standard deviation is 57. So we'd be counting 57 each way. 3 times 57, 57, 57. So this would be, and 57, that would be 1607 and so forth. This way I would subtract 57. That would make that 1,500. That would make that 1,493. So 1,500 hours would be about here. This would be 1,500 hours, which is below the average. So that's a good advertising. You wouldn't want to advertise above the mean. And we want to know the probability that if I pick a light bulb, what probability of light bulbs out there will last less than the advertised time? So how many of them fall into this category? So the probability that X is less than 1,500. And so now that we know that we can do this in the calculator and we don't have to normalize and find the z-score and all that, we're going to be using that normal CDF. So second distribution, normal CDF, and the lower boundary would be negative infinity. So -1 E99, that's negative infinity, up to 1,500. The mean was 1,550, and the standard deviation was 57. It says it's 0.19. So that means 19% of light bulbs last less than the advertised time. That's not bad. Now, what's the probability that a light bulb would last more than 1650? So more than 1650, whoa, that's a bad picture. 1550 would be here. So 1650 would be more like right here, 1650. And so we're talking about this region. The probability that X is greater than 1650. The distribution, CDF. More than 1650, the lower boundary would be 1650, and we would be doing positive infinity, which the calculator knows as 1E99. And I get 0.039, which is approximately 0.04. That means 4% of the light bulbs last longer than 1650 hours. Or you can think about it as a randomly selected light bulb. There's a 4% chance that a randomly selected light bulb will last longer than 1650 hours. What is the probability that a randomly selected light bulb will last between 1625 and 1725? Oh, so we're wanting light bulbs that last a long time, huh? So 1625 would be around here. 1725 would be here. So we're talking about like this range. Okay, so the probability that we're between 1625 and 1725. $16.25 and $17.25. And I got 0.093. And that means only around 9% last between blah, 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 blah. Or the probability of selecting a light bulb in that range that lasts between 1625 and 1725 hours is 9%. What is the probability that a randomly selected light bulb will last longer than 1400 hours? Okay, 1400 would be way, way, way over here. So more than 1400, now I'm guessing that's going to be pretty high. So I invite you to do this one kind of on your own. I'm not going to show my calculator, so I want you to try it. And I got 0.9957. That's pretty darn high. Now, how long will a light bulb last if it is in the top 15%? Now, I haven't shown you how to do this in the calculator yet, I don't think. This is a different option in the calculator. So let's think, the top 15%. Now, top 15% would be, this is 15%. In the calculator, we have to tell it the area on the left, sort of like we would in the table. So the area to the left of that is 85%. And we're going to go back into the distribution menu to something called inverse norm. Inverse norm, because it's doing the inverse, we're giving it the area, and it's going to give us the value. So let me show you what you're going to see on inverse norm. It says area, and it wants the area to the left. So the area we're going to put in as 0.85. And then it says mean and standard deviation. Well, we know those. That's 1550 and 57. So 0.85, 1550, and 57. And it gives me 1609. What is the length of time a light bulb lasts if it is at the 8th percentile? Now, did it say it was in the top 8th percentile? It didn't. So 8th percentile is actually talking about 8% here. 99th percentile would be way up here, or 92nd percentile. 8th percentile is way, way, way down there. So we would change the area to be 0.08. 8th percentile is very low, and that would be that would round up to about 1470 hours. Let's look at another example. Suppose that the blood pressure of men aged 18 to 29 years old have a normal distribution with mean 120 and a standard deviation of 10. What value of blood pressure is in the 75th percentile for this population? So let's think about the picture here. I want us to always think about what the picture looks like. Okay, so mean is 120, standard deviation, this one's easier to do. We count out 3 in each direction, so this would be 130, 140, 150, 110, 100, and 90. Now, where would the 75th percentile be? 50 percentile would be right in the middle, so 75th is going to be somewhere in here. So 75% would be below. So we would do the inverse norm again. So this would be inverse norm. And we would do 0.75. And the average was 120 with a standard deviation of 10. And it says that it'd be 126.7 blood pressure. Would be the 75th percentile. Okay. A pediatrician obtains the heights of her 200 3-year-old female patients. The heights are approximately normally distributed, with a mean of 38.72 inches and a standard deviation of 3.17. The pediatrician wishes to determine the heights that separate the middle 98%. So in other words, we want to find the first and the 99th percentile. So the top 1% and the bottom 1%. So we have our middle is 38.72, and we want to know where the cutoff is, that 1% is below and 1% is above, and that 98% are in the middle. So let's think how we would do that. For this one, that's easy. We would put in the area as 0.01. And the average was 38.72. And what was the standard deviation? 3.17. So this boundary is 31.345. And the upper boundary, what would we put in for the area for that? How much is below that marker if 1% is above it? Well, that would be 0.99. And that is 46.095. So the middle 98% are between 31.345 inches and 46.095 inches. Next, let's suppose that men's foot lengths are normally distributed with a mean of 25 centimeters and a standard deviation of 4, and women's are normally distributed with a mean of 19 and a standard deviation of 3. Sketch both curves on the same axis and label them. Okay, so this is kind of why we've been marking these very well. So if we've got to go, let's see, mean of 19. I'm going to count let's make this 10. 20, 30, 40, and then let's see, that should be good. So for the men, let me do two different colors here. I'll do red for men. The mean is 25, so that's going to be right here, and the standard deviation is 4, so that would mean we go out 4 here. That'd be at 9, 4, 23, 1, 2, 3, 1, 2, 3. So that would be the top of the hill, right? So do something like this. This is for the men. For the women's foot length, they're normally distributed with a mean of 19. We'll use purple. So the mean is 19. And a standard deviation of 3. So if I add 3, I'm at 22. Add 3, that's 25, 28. Go this way, 19, that makes it to 16. And so 1, 2, 3, something like that. So here's my high point for the women, and it goes down, and then it goes down here. And so this is for the women. What is the probability a man's foot is smaller than 22 centimeters? So remember, for the men, it was a mean of 25 and a standard deviation of 4. And smaller than 22 would be doing the probability of x is less than 22. So that's a normal CDF. Whoops. Normal CDF. Lower boundary is negative infinity to 22. And we get 0.2266. For the women, mean is 19. The standard deviation is 3, and we want to know what's the probability that their feet are greater than 22. So change that to 19. I got 0.1587. Oh, and we have a typo. What size foot would a man in the upper, that should say 5. I don't know what happened there. Percent of all men have. So we're talking about, okay, upper 5% would mean that there's 95% below. Okay, so men, gotta go back. We're doing inverse norm. Area would be 0.95 because it's to the left. That's 31.58. That's centimeters. What size foot would a woman in the bottom 10%? Bottom 10% would be 10% here. So inverse norm, 0.10. The average for women was 19. Standard deviation of 3. 15.16 centimeters. And so that's how we can use the standard deviation to solve application problems.